And now here we have the new vertex and its neighborhood is a clique. That clique may be a maximal clique by itself. In that case, just the neighborhood n of v, if you take v, the so called n of v, the set of neighbors of v will be a maximal clique somewhere here, right. So, somewhere it will be, maybe this one, right. Now, what we can do? We can add v to this, because that will only, that is the new maximal clique, it is a bigger maximal clique, because if v was like this and this was a maximal clique, nothing more can be added to it from the other part, the already seen part, but this can be added, no, because this vertex is adjacent to all of them, right. So, that means we can be added to that, but it is possible that this n of e may be part of a clique, maybe only this much, that is possible, no, sometimes. That means if I add v to it, this is not even a clique, right, because v will not be adjacent to this part, but v is adjacent to these parts. So, therefore, what you should do? You should collect this portion, so and then attach something here. So, not that you remove it from there, it will be there, right, it will be there also, but this part will go to here and v also will be there. We will get a maximal clique like that, because v is adjacent to all these things. Nothing else can be added to that, because that is a maximal clique, because v is not adjacent to anything more, right, that is the only thing. So, therefore, v guarantees that the new thing you have created is a maximal clique. So, you have not destroyed anything which you have created till now, but just that you have added one more maximal clique, but connected it to this where you detached, you collected a few vertices, no, to that would not be connected. Now, the other property is also satisfied. Can you see that? Namely, if you take a vertex, any vertex, say u, still those maximal cliques in which u was appearing is still connected, because if it is already, if it is that part is only in the earlier part of the tree, then there is nothing we have changed, right. But only problem is, suppose it was that u is part of these vertices with which we created the new bag. Now, no problem, because u is anyway here, it was connected in the earlier part and it is also connected to this. V as such is appearing in only one bag now. So, therefore, it is by trivially a connected part, right. So, I hope you are following what I am telling. So, what I am trying to do, I can see you for the caudal graphs, I am making a tree of maximal cliques. It is not a tree, it is a conceptual tree, because each tree node will correspond to a bag of vertices, a set of vertices which essentially forms maximal cliques of the caudal graph. And my claim is that this tree can be formed with the extra property that if you look at a single vertex and identify the bags in which it is part of, it will be part of many bags, because we are not saying that each bag is disjoint or something. A single vertex can go in many different bags, and then these bags should form a connected part of the tree that we are making, right. And I have given you a very simple construction for this thing, just that keep looking at the order of the perfect elimination ordering in the reverse order, and then keep adding it, right. And then when a new vertex appears, look at its neighborhood. If its neighborhood itself was forming a full bag, then just add this vertex to that, because that is fine. Actually, the maximal clique should contain this also, right. If it was only part of the bag, then that part of the vertices, that n of v, along together with this new vertex forms a new bag. Does not mean that the earlier bag is destroyed or something. Earlier bag remains as such, but we created a new bag and connected to where it should connect to, where it came from, and that is it. So, this is the construction in which so this way we can construct something. So, the details of this thing I am not worrying too much about the this thing. So, then so we essentially following this algorithm we get such a tree. So, you know, this corresponds to the so called tree decompositions. Why tree decomposition? So, tree decomposition needs the following properties, namely each vertex. So, this tree decomposition is not only for caudal graphs, it is defined for all graphs. So, each vertex V should be part of a bag, right. That means we cannot discard any vertex, it should be part of at least one. So, in this construction we are adding each vertex in at least one bag, right, and each edge UV should be in some bag together. U and V together should appear in some bag. Simultaneously U and V should appear in one bag. So, in this construction also we are making sure out of U and V whichever is the lower numbered vertex, when that is being considered, its neighbor in the neighborhood of it will be there, right, in the neighborhood of it U and V will be there. So, the third property is what we were telling, namely if you take any vertex U and look at the bags in which U is part of. So, this should form a connected subtree. This is the so called continuity. That means, if U is there in a particular bag and U is there in another bag. So, the path in the tree, right, there is a tree, there is a path to go from this bag to that bag now. And all the bags in that path should contain U, right, that is you cannot abruptly disconnect it, right. So, our the tree we constructed here for caudal graphs correspond to a tree decomposition, that way, because these properties are, but then when we do it for caudal graphs, there is an extra property. What is the extra property we are getting? The bags are maximal cliques, but in usual graphs it may not happen. Usual graphs bags may be, may not be any structure in the bag. If you look at the bag, yeah, that may be just a collection of vertices. When you construct a tree decomposition, there are various ways of constructing a tree decomposition. In fact, you can put all vertices in the same bag and say, okay, this is a one node tree and this is a tree decomposition. That is also valid, because all these conditions will be trivially met. That is a useless tree decomposition. Usually, when we construct a tree decomposition, our concern will be to minimize something. What will we try to minimize? We are concerned about the bag sizes. Look at each bag we created and look at the biggest bag among them, and we want to make sure that the biggest of the bag is minimized. Right? You do not want any bag to be too big. So, that means the maximum bag, the biggest bag we should keep as small as possible, right. So, if you keep the biggest bag as small as others also will be naturally be small, right, because others are at least smaller than them, right. So, it is not necessary that all the bags are very small, but one bag is too big, that we do not want. We want like the worst case to be controlled, right. So, in this case we know in the tree in the caudal graph case we know that this is the maximal clique. So, the maximum clique will be a maximal clique. That maximum clique will become one of the bag, that will be the biggest bag the way we have constructed, right. And it is easy to, like from this definition, if you struggle a little bit, you can show that you cannot go below this thing. When you try to make a tree decomposition, one of the bags, so because the cliques should go anyway in one bag together, there is no, there should be a bag containing a full clique. So, therefore, one bag should be as big as the maximum clique, right. So, in the caudal graph case, we are getting this good tree decomposition, optimal way of decomposing, right. Now, let us see the once you know that for given a caudal graph, so this nice tree can be nice tree decomposition can be obtained. Now, from this thing I will show you how to get the intersection representation for the given caudal graphs. What I have done is I have taken a caudal graph, constructed this tree decomposition where each bag is essentially a maximum clique, right, and all the properties of the tree decomposition is valid. Now, my point is this conceptual tree. So, you can forget that each bag is actually contains a lot of words, but think of it as a tree. Each bag in your mind should only look like one single vertex for something. I mean that vertex does not correspond to the vertices of the caudal graph you are dealing with, right, because essentially that is a bag, right, that is a bag of vertices from the original. So, this conceptual trees, subtrees we can define corresponding to each vertex. How will you do that? Take a vertex of the caudal graph. So, of my caudal graph G, so I will say V comma E. This is the given caudal graph. So, for this thing I have this conceptual tree I have defined. So, now take any u element of this V here, and then in this tree, remember each vertex here in this tree is a bag. Now, look for all those bags in which u is part of, say Bi1, u is element of Bi2, so u element of I3 and u element of Bik, suppose some k bags I identified in which u is part of. Now, see the induced tree on those vertices corresponding to those bags alone. We know that by definition of the tree decomposition, the way we have constructed, that should be a tree structure, connected structure, right. So, that is the subtree corresponding to u. So, I can call it Tu or something, T, it is a subtree of T, right. And like that for each vertex here, a vertex of the caudal graph, we can construct a subtree in the conceptual tree we created. Now, if I claim that if I make the intersection graph of these subtrees, I will get back this caudal graph. Will you agree with me? So, to remember, we are given a caudal graph G, and from that caudal graph I constructed a conceptual tree where this conceptual trees each vertex correspond to a bag of vertices of the original caudal graph, and it satisfies so many properties, right. Namely, each bag induces a clique, a maximal clique of the G, and there is this connectivity property and all those things. Now, I am claiming that, see look, the given graph caudal graph G is essentially an intersection graph of some subtrees of this conceptual tree, Which subtrees? So, we have to make a list of subtrees. The universe is based on this tree. From this thing, I will make many subtrees of this tree. One subtree corresponding to each vertex of the caudal graph, right. So, Tu, right, for u element of V of G. How am I making the Tu subtree? I am just collecting the bags in which u is part of, and in the conceptual tree each bag is a node now, right. So, that forms a connected structure there. That connected structure, that connected subtree is this TU, say, that I will associate it with the U, and for each vertex I got. So, how many, for if there were n vertices in the caudal graph, I get n such subtrees, right. Some of them may be intersecting, some of them may not be intersecting, right. Now, my claim is that keep your original graph where you started somewhere for reference, but now look at only these subtrees you have created and make the intersection graph of these subtrees, just for checking whether there is something in that or not. Yeah, we will get back the graph is what I am saying, right. Why do we get back the graph? But we have to do two things. Take two vertices, u and v of the original graph. The corresponding to that, now we have tu and tv. Now we have to show that if u and v had an edge, then tu and tv intersect. If u and v did not have an edge, and tu and tv will not intersect. This we have to show. So, if u and v had an edge, then we know that there is a maximal clique containing both of them together, right, because that is also the property of the tree decomposition. There is some bag in which both of them are coming together, and then therefore, that is a maximal clique. So, there should be an edge, so that edge, right, and then tu and tv should intersect, because that vertex at least where u and v came together is part of both tu and both tv, right. So, there is an intersection between tu and tv. On the other hand, if u and v did not have an edge between them, they cannot come together in any vertex. Why? Any bag, because if they came together in the same bag, that is a maximal clique. In the maximal clique u and v came together, that means there was an edge between them, which contradicts the assumption that u and v were non-adjacent. Agreed. So, this is somehow this construction correspond to the original graph. We get back the original graph, right. What I have done is given any caudal graph. So, I have shown you a tree which we made by an abstract consideration of bags and all, and some subtrees of that tree such that intersection graph I make out of these subtrees will correspond to the original graph, right. So, for any caudal graph you have this structure, right. So, therefore, caudal graphs happens to be the subtrees of some trees, right. So, now if you want to show that if C4 cannot be represented as the subtrees of a tree, just try doing that. It just intuitively you can understand that, right. Suppose if you have a tree for u and then v is adjacent, they should intersect with these things, go somewhere else. The third one intersects, but then how will you make it the third one intersect back with the first one without intersecting the middle one, right. So, that if you imagine a little bit on the tree, you will see that no, that is not possible, because it is approximately like that interval graph argument. This is tree, there will be a lot of things, but still you know that there is only if you want to come back to the original, then you have to hit the middle, right. So, what I have done, I was telling that caudal graphs also is an intersection graph representation. Now, again coming back to the intersection graphs. Coming back to the intersection graphs. So, we started from the interval graph. Interval graph is usually a starting point for many things. The caudal graphs, subgraph is interval graphs. Many other class of graphs are defined from interval graphs. So, I can tell some examples. One is if you want to generalize. Now, interval graphs are like on the real line, I take intervals, right. So, this is real line, you take intervals and say the intersection graph of intervals is on the real line is the interval graph. Now, why real line? Maybe we can go to a circle like this, no, it's ellipse, but if I draw better it will become, right. So, then see intervals can be on these things, arcs, right, on this on the circumference of this, So, many intervals can be defined on this, right. Does it make a structural change? So, is it the same as the interval graph? From the real line is now I make both ends meet. This is called a circular arc graph. Circular arc graph. Intersection graphs of arcs on a circle, right? Intervals on the circumference of a circle. This is structurally very different from, actually, though it looks similar. So, for it's not even a perfect graph. It's not a caudal graph, because you can see that very easily you can make a C4 here, see, like this, right? C4 came, right? But in interval graph that was not possible. And not only C4, you can make C5 also, same way. So, which means that it is not even a perfect graph. So, now just by making the real line like a circle, right, and considering the same thing here, you lost all the structure which we had, the nice structure we had on for interval graphs we lost. It is not even a perfect graph now. And not all interval graphs are still circular R graphs, but there are only subclasses of circular R graphs. But the minute they tried overlapping through the other side, we have lot more complication, right. So, this is a class of graphs where it is considerably more difficult to do things. Okay. So, I do not want to get too much into the circular R graph, but wherever you try to do something in the interval graph, you can see whether you can extend it to circular R graphs. It is much more clumsier to work in those things, because so now intervals keep interacting from both sides, right. You have to keep track of both that. And that is going up. There is some way of considering subgraphs of interval graphs also. The most natural thing is to put some restriction on the interval graphs. For instance, you can tell that all intervals are of same length, very neat, right. You do not allow things like one like this and all. So, everything should be of the same length. Then we will say they are unit interval graphs. That is because we are assuming that they are unit length. Or as long as it is equal length, it is the same thing. Structurally, there is no difference, right. Unit interval graphs. You can see that in a unit interval graph, not even this thing, see, is a unit interval graph. Can you show that? See, we saw that a star was an interval graph earlier, no? But once we insist that all length should be equal, then even this cannot be represented. This 3, it is called a claw. Why? Because if you put the central vertex here, you have only 2 endpoints. Now, you can put one here, and the third one should be put in such a way that it does not touch this or this, right. That means you can only put it like that. It will become smaller than the length, right, because all have to be of equal length. That means it will always touch this endpoint or this endpoint. That means 3 things cannot be put the pigeonhole principle, right. If you put 3 of them, at least 2 of them should be either in the left endpoint or in the left point, right. That means they will intersect each other, but here we have an independent set. These edges are not there, right. So, that means that restricts the interval graphs quite a lot. You can actually show that if this interval graphs which does not have claw are exactly the unit interval graphs. So, we will do it in the next class, whatever, right. This is